All right. So as people are walking in, so how's the day been so far? Yeah? So we've spent most of the day, obviously, talking about the language and sort of the front end. And so we thought it would be a great idea to bring a fellow by the name of Jim Radigan out here. He's an architect on the Visual C++ backend compiler team. They're the guys that build c2.dll, which basically generates the optimized code for the machine that it's actually going to run. So he's going to take us through how his work is evolving. And we kind of want to give you guys a break from the front-end language stuff and learn about what happens really close to the machine. Jim Radigan.
Hi, everybody. I'm Jim. I've been at Microsoft for 15 years. I'm the architect and now the dev manager for the C++ optimizer and a few other things that they've tacked onto our team that have to do with analysis and code generation for other runtimes. But Charles asked me to come and talk today about basically how we're evolving the compiler. So specifically, what we're going to talk about today is evolving the C++ backend for Microsoft. And the reason I say for Microsoft is because there's one point that I want to really try to get across to the audience is how big that job is and how it's heavily constrained. So how many people remember the Pentium? Anybody out there? Anybody old enough? All right. That's about 3 million transistors, okay? So now, if you remember, that was a really big deal in the day because that was the first time it was a superscalar. Well, almost a superscalar. It was 2 pipelines, and if you actually repeated the code in the back edge of a loop, you would actually get the hardware to execute some instruction-level parallelism. And it was a really big deal in the day. We went through an enormous amount of stuff to line things up properly in the code so that that chip would hit both those pipelines at the same time. So now, fast forward to today. If you bought a chip before the 4th of July weekend, you're probably running on an Ivy Bridge. Okay, that's 1.4 billion transistors. So if you want to think about scaling the Pentium, which was 3 million transistors, to this today, that's that black dot. Right there. So that's an enormous amount of hardware that's available to the compiler to control and to exploit. And if Herb is here, it's to maintain correctness in semantics at all times. Even the ARM chips are getting complicated, right? I mean, and that's old, right? Both NVIDIA and Qualcomm have forged ahead dramatically from this point. This is the Tegra 3 in the original Surface, and that's 5 cores. That one extra core on top is where the chip will throw your app if it's really something that can run low power. But still, the other 4 cores are 128-bit vector machines. So I tried to figure out a way to graphically represent what this talk was about in one slide, because I think it's really important to get that key thesis across right away. What we're going to talk about is evolving the red arrow. Okay, and let me explain why. So compiling at Microsoft means mapping that to that hardware. And if you think about it, I just heard this on Bloomberg. For the last 5 years, $87 billion of Windows licenses have been sold. You can get Windows. We might not be that prevalent in all the places that the press talks about lately, but behind the scenes, Windows runs banks, brokerage houses, airports, my son's high school, the internet. It's everywhere. And it's got to be mapped to an ungodly amount of hardware, different and disparate with different run times. And if we're selling that much on the software side, we're well over $100 billion in that same period of time for the hardware. So that red arrow is the compiler. And that red arrow really, really, really is important, especially to this company. So if I talk about evolving the compiler, we really, really care about compiler throughput, absolute correctness. Now, I just wanted to see if anybody was awake. All right, so everybody's still with me. Code size is a really, really big deal. And then code quality. So that's really what that red arrow is all about. So if you look at the functional block diagram of the Haswell chip, we have to figure out how to map C++ correctly and efficiently to 4 cores, and each one of those cores has 256-bit vectors. And soon we're going to be looking at being able to map C++ to the huge chunk of real estate on your left, the graphics processor. So mapping Windows to that hardware is a really, really difficult and incredibly constrained problem. And so when I talk about evolving the compiler, I want to talk first about how we work, how we don't break things. That's probably the most important thing we do. Then I'm going to talk about some of the core technologies that we really care about evolving and have cared about evolving for the last 2 years. And then I'm going to talk about where we're going. So first of all, when I talk about how we work, we compile all that stuff, right? So above all else, we're responsible for mission critical correctness at all times and for compile time. Because if we slow the compiler down, we actually burn more servers to actually build the software in the company every day. So these are the 2 points that are most important, correctness and compile time. Anybody have any idea what that is? That's 24 cores pegged, that's 32 gigabytes of memory on that machine, and it's got 3 RAID 0 drives. Yep, that's right. That's compiling Windows. That's one machine compiling one copy of Windows. So that's one build, and that isn't even when we haven't even started to run Windows yet, but that's what we do for one architecture. And then if we're really, really in a hurry, that's 40 cores that's pegged building Windows. And we have 2 of those in our lab. So this is a visual of what we actually build using those machines. So we have to build Windows for x86, for ARM, and x64. And then for each of those architectures, we have to build a retail build and a checked build, which has an awful lot of extra runtime checking going on. So there you go. There's 6 machines. And so if you zoom in, you can really begin to see the 24 core machines, the 80 core machines, all being used differently. Your top left-hand corner is building the x86 checked. The bottom left-hand corner is building an ARM retail build free of checks. And we do this every day. We kick this off at about 3:30. And that's for the live compiler against the live version of Windows. And so for the last 2 years, we've been evolving how we work to get here. And this is probably lately the single most important thing, and it's also the biggest thing that I'm proud of, that we actually got the team to do this on a regular basis. So now we're at a level of correctness always where we feel that we could ship the retail compiler if we had to within about a month to 6 weeks. We could lock down, really stress it, and be done. So now we've got predictability, which is a really, really big deal. And what's really great then is that internally the teams have begun to trust the compiler team a lot more and are willing to take really, really late updates for the internal tools that we give them to build either Windows or SQL or Office. So if you're a compiler developer, this is where you go into denial. You build all 6 flavors of Windows, nothing went wrong, great. So if it's Friday, you go home and you live in denial, right? So now what do you do after you build it? So what we do is we actually take the version of Windows that was built through a whole bunch of automation between our team and the Windows team, and we install Windows on a VM, and we call that a staged build. Then we throw in the inbox applications on top of it, and then we shoot that off into a sea of about 750 servers, and we stress the hell out of what we just built. So if you look, I just wanted to give you an example of some of the automation that we throw at the build that the compiler just produced. So if you look, you can actually see, we'll throw the Safari browser on there, the Google Picasa, we'll put on Google Chrome, WinZip, Sony Vegas Movie, the Java runtime from Oracle, all of the internal Microsoft applications, and then we'll run this. So the blue screen to death, if you're a compiler developer, is really, really a painful day. So you don't want to check your stuff in and then try to get the compiler to build Windows and for it to be stressed unless you're really, really sure whatever your optimization is absolutely correct. Because once a compiler developer hits this, he could easily go off the grid for about 2 weeks. So it is very definitely a lifestyle choice. It's great, though. Windows 8 has improved the blue screen, right? We were one of the early developers. We were one of the few people to find out first and early that was an improvement, and that was great. It seems much more forgiving, right? So we talked a little bit about how we work, and I thought it was really important to stress how large the problem is, because it's an enormous amount of infrastructure and an enormous amount of testing that goes on daily. Every 3:30, we kick off whatever's been put into the compiler and just stress Windows, as I just talked about. And we do that with SQL as well. And we do that with a few other partners internally so that the team can scale. We get a lot of help from our partners over in Office or to a few other teams that I can't drill into right now. I'd like to, but I'd like to say thank you to those teams. So now, what I want to do is talk about the core technologies that we evolve within the context that I just talked about. Okay? But before I start, it is a business, right? So one of the things we can't do in our space, because of all the targets that we have to hit and for all the testing that we have to do, we can't tolerate any switches for adding any new optimizations or for partially turning one off or turning one on. So each switch that we add to the compiler is really well thought out, because it's easily going to add a couple of $1 million a year just to the testing. So everything we try to do and evolve in all the technologies I'm about to talk about have to be on by default. So these are the core technologies that we really care about. Code size, stack size, and data alignment. I glom those together into one bullet item in order to just save time. It'll be one section of the talk. Then we care a tremendous amount about vectorization, parallelization of existing C++ unaltered C code. So what we have to do is look at 20 years of legacy code and try to extract parallelism from it and not violate the semantics. We care a great deal about security, and I'm going to go into security as much as I can without getting in trouble. This has been a heavily edited part of the slide deck. So if it's not 100% clear, that's by intention. But I'll be happy to answer questions. Then another thing that's really, really important, especially since it's C++, is parallelizing control flow. There are very few loops in C++ that don't have if then else. And then finally, I want to close with alias analysis. That's a big part of where we're going. And I want to show how important alias analysis is. And all of this, all these core technologies are really, really important for all of the hardware and all of the runtimes that we target. Sometimes I actually feel it's harder to target the runtimes, the myriad runtimes that we deal with, than it is the different hardwares. So I'll drill first into the code size and stack size and data alignment. So this is an example of a program where we're going to do something called stack packing. And if you look, it's got 3 local variables. And for various reasons, we could actually, it's got 4 local variables, sorry. W, X, Y, and Z. So we could, if we had to, create just 4 stack slots, 4 locals. But if you look, that's going to shorten the lifetimes for a couple of things. And if you see Y's lifetime only begins well after that we returned if we took that control flow path. So in this particular example, what you can see is that we could save 1 stack slot and pack Z or Y into that 1 local frame. Now you might not think that really means a lot, but when you're in the domain of code size, the currency you care the most about is cache lines. So packing Z or Y in there saves a word. If you're on a 64-bit architecture, it saves 64 bits. And this adds up if you have a lot of locals and you're in the kernel, or if you have a deep call stack and you're in something like JavaScript walking the DOM. This really adds up. So here's an example where I personally broke stack packing. And it took a month to figure out why something slowed down by 4%. That was a poor lifestyle choice. I'm using HR terms because our HR person is watching this. So what you can see is the code on your left is what the code was like, its code size before I broke stack packing. And then on the right is how it got bigger. And those R's are the reasons why stack packing led to a cascading sequence of errors, which basically bloated the code. And because this chunk of code that doesn't contain a loop blew a few extra cache lines repeatedly for 1 billion times, something slowed down 4%. And if you're on a phone, that matters a lot. If you're doing anything that's touch sensitive, the feel and the experience you get, that matters a lot. So just to drill in really quickly, you can just see reason 1 is where we actually generate the code to create a stack frame when on your left-hand side previously there was no stack frame. So stack packing would have allowed us to actually get away from not creating the frame. So it's all about cache lines. Here's an example of JavaScript and MS-HTML. And if you look, that's in WinDBG. And on your left-hand side are the bytes for the frames. So if you're taking a deep dive like that and you're repeatedly walking the DOM, you're burning cache lines and maybe even pages. So that really, really matters. Here's a great example of another routine. This is old, so I can't get in trouble. This is NTFS common read. So if you look at the number of locals in there, it gets pretty large, right? So that you can think of that being a problem of saving space in the kernel. Problem is, though, that's the bottom of the routine. Right? So now all of a sudden, you have to worry about asynchronous control flow. So structured exception handling allows you to wrap code, and actually you could be taking a control flow path now asynchronously from any line of code to just about anywhere you could imagine. That's exactly what you have to worry about. It's great for writing operating system code to handle media failures or hardware failures, but when you're doing compiler optimization, the flow graph gets really complex because you got to model all the control flow. So what we've done is we've abstracted away the code first to create a region graph. So that's the outermost try except. That's the root to represent the region of code that's not surrounded by any exception handling. And then the inner try finally is nested within that. And this data structure is essential then for being able to reason about all of the lifetimes in the program. Because now I can reason about whether or not X is going to be preserved by the runtime, or whether or not I really have to worry about two lifetimes possibly overlapping. So what the compiler does is it starts out by saying, okay, anything that's involved in the exception handling, we take the address of it and assume that it's been globally aliased. And then what we do is we use the region graph to go through and reason about whether that address taken really needs to hold based on the properties for the nested exception handling. So what we've done is we've come up with a paradigm to allow us to model asynchronous lifetimes in the presence of exception handling in order for us to do stack packing, and it really, really matters in system code. But we have to get it right all the time. So we can't really take a lot of chances, and that one took probably about, once we had the algorithm to get rid of every single bug, I would say it took at least another 6 months of just baking. We call it bake time, to make sure that it had been stressed and we trusted, and that's on by default in the compiler. So we talked about code size, and now I'm going to just abruptly go into vectorization and parallelization of existing C++. You saw the size of the chip and you saw all the cores, so you can imagine that we've had to recently put an enormous amount of time into being able to extract parallelism, especially from the legacy C++ that's out there. So I just wanted to give you an example of a demo where we, if I don't screw this up. So that's just a simple ray tracing program, and what's going on is that the vectorization really matters for the glow. We've taken unaltered C++, vectorized key parts of the loop that take care of the glow, and then we've spread the parallelism across multiple cores. So what's interesting about this is that that ball would actually bounce up and down maybe 1/100th as fast as you can see there. What's going on right now with this demo is that we've just taken unaltered C++ and automatically vectorized it and automatically parallelized it across 40 cores. And if you look at the status, we've got all 40 cores pegged 100%. Thank you. I know it's been a long day. So for those of you who are not familiar with vectorization, what's happened is that the CPU has created 128-bit and 256-bit wide registers and then machine instructions to operate on those. So for example, that's a simple vector add. So what you can do is on a 128 vector register machine, you can add 4 floats at once or 4 ints at once. Pretty straightforward. So what will happen then is if you have a loop, you can actually do it in 1/4 the time. And so if this hits, it's really, really a big deal. So what we do in the compiler then is we take a simple loop like that and we try to map it into something like this. And that's an example of the machine code we would generate if we didn't know whether or not A, B, and C were perfectly aligned at 0 mod 16. So in order for the compiler to do this, it has to look across loop iterations to figure out if it's legal. So what we do inside the compiler is we build that really complex mathematical model. We take all of the loops that wrap a statement or a load or a store, more specifically. And for every load and store in the loop, we build a symbolic equation that's a function of the containing induction variables in the loops. And then we have to prove that those induction variables start at a known value, end at a known value, have a known stride, and that induction variable is monotonically increasing. All of a sudden, then, this becomes a linear algebra problem. So we can model this in many different ways, but the big engineering task, remember, we can't have any switches. The big engineering task for the compiler here was to build that complex equation for every load and store in a loop while building Windows or SQL or Office, because it's all on by default. So the reason why we build those symbolic equations and jammed a tremendous amount of math in the compiler was to see if it was legal to vectorize. So one of the things that you have to wrap your head around quickly to understand why we needed the math was that sequential loop is not equal to that vector loop. And what we'll do in the compiler is prove why. So it's easy to understand this if you try to figure out how A sub 3 would be calculated. First in the vector loop, and then second in the sequential loop. So what we'll actually do is model the dependencies between A and A sub j minus 1, and then we'll vectorize it to turn it into something like this, but it's not legal. So vector semantics, if you look back to the machine, require that all loads happen before all stores. So in this particular example, we would load vector register 1 with those values, vector register 2 with those values. Vector register 3 would be the vector add, and you would see that A sub 3 is a function of A sub 2 and A sub 4. And then we'd store that back into memory in those locations. So it's important to see that the vector version of that instruction is going to be a function of A sub 2 and A sub 4 for the third element, okay? So now, if you look at the sequential loop, and I won't animate that, fortunately, you'll see that A sub 3 is a function of A1, A2, A3, A4. So clearly, that's a visual for why we've got to do the math to prove that it's legal to vectorize. So basically, we doubled the size of the optimizer and its analysis in order to actually model simple equations like this. And it was really a painful thing to do because we had to do this without really seriously impacting compile time or correctness. And a lot of times we'll throw this analysis at a loop and it'll disprove that it's legal to do vectorization or automatic parallelization. So we have to tear down quickly. Because you can imagine a tremendous amount of C++ doesn't have legal parallelism in it. So if we have to do symbolic math, and we have to do that on C++, clearly there's a collision. So that's a good example of just some complex C++. We've got to be able to figure out how to actually map those mathematical equations on all the loads and stores in that loop, and then look across iterations and successfully reason. And that's something that we do handle today. We do automatically vectorize this and parallelize this. So let's go into a couple of the problems. We spent about a year just building the infrastructure to handle parsing C++ and getting it into a form to tell whether or not it was legal to parallelize. So it gets more and more complex. For example, in C, traditionally things are passed in as parameters. So in this example, A, B, and C, the base of these quote aggregates, or what we hope would be arrays, is unknown. And we don't even know whether or not A, B, and C overlap. Here's another one. Forget about the pointers being passed in. Where's the induction variable? So we have to build symbolic mathematical equations on every load and store, and those equations have to be a function of an induction variable that's monotonically increasing and well behaved for that loop. That's an important loop too. That's something that appears in the STL library down low. So remember, somehow we got to be able to do that in order to vectorize that loop symbolically. So, and then turn that into a series of vector instructions. So what we've discovered painfully early on is that parallelizing C++ requires transformations to the source code internally just in order to do the analysis. And engineering that correctly while building all the software in the company and not affecting the throughput was a really major undertaking. So let's just take a look at what I mean by transforming that loop in order to do analysis. So that's the core body of that loop. What we first have to do is transform that and create a synthetic induction variable and a synthetic upper bound. Because what we're going to want to do is run this loop off of an induction variable we can use for symbolic equations. So that would be the new loop that we create. And that would be how we sort of faked up array references. So now I've got what looks like a well-behaved loop to begin the analysis. So we've done all of that transformation internally before we've even decided whether or not we're going to go parallel or vector. Make sense? All right. So we did the analysis, and we decided it would be legal to vectorize this, but we have a long way to go still. We don't know if the array bases overlap. We don't know what the target instruction set architecture is going to be for the binary that we're going to be producing, right? We're going to produce code that can run on machines that are maybe 8 years old, or we could generate code that targets Haswell. And then we don't know whether the trip count itself is something that can be divisible by the size of a vector register. So here's what we'll do when we generate the code finally. So if we were to just assume that that's a way of representing a vectorized instruction for the inner loop, we'll do 4 at a time, and that's traditional Fortran 90 vector notation for the arrays, happening all in 4 at a time. So what the compiler will do is it'll actually generate code that gets executed at runtime, which will test whether or not there's overlap between the store and any load. So we'll test at runtime, and we exploit the fact that everything's super scalar and bury a lot of the latency to see whether or not basically the beginning of result points inside first 1 or first 2. And if that's legal, then we'll insert some runtime code. If we wanted this binary to run only on Haswell, lit up as vector code, to see if that at runtime, that instruction set was available on the architecture. So what we do is we change the C runtime to actually initialize a global variable for us called ISA available, and then we test it with the code that we insert. And then if we ran that loop in vector and we don't know what the upper bound was, whether it was actually really 0 mod 4, we have to execute a cleanup loop that would run sequentially, or we would just simply run that sequential loop if there was overlap or if we weren't running on Haswell. So this technology that we've built really maps C++ to all forms of parallelism. Vector, and multi-core. So what we do is after we vectorize the code, we then pass it on to a later phase, which will rip out the loop bodies that have been vectorized and fling them across the cores. Or SPMD, which is meant to be for the graphics or the GPU side of the world. So we're really interested in actually now expanding this technology to actually go after the SPMD model of parallelism on the graphics cores. But we have to do all of this without worrying about the blue screen of death, because above all else, it's throughput and correctness. So we talked about vectorization, parallelization, and now I'm going to talk about what some people call the darker side of C++. So I'm going to go through an example of heap overflow. All right. So this is a chunk of code that was in its day really famous. So what happens here is we're going to set that variable to 4,470 bytes. Then we're going to allocate that buffer. We're going to allocate 4,470 bytes. Now we're going to reassign that size to be 4,496. And we're going to get exploited. So here's another really exciting piece of code. This led to a lot of press. This is about, I would say, 3.5 years old, this exploit, so I'll still be able to leave the room and have a job. This is how this worked. So we're going to pass an onload event to a function, f1. Then what we're going to do is we're going to copy that event data structure, and we're going to forget to do an add ref. Okay? Recall that all the red is written in C++. Then we're going to destroy any remaining uses of that object, so that basically it's going to be freed and then it's going to fall out of scope. And then we're going to call something to fire asynchronously. We're going to call F2 to asynchronously fire. So EVT really does go out of scope at that point. And then later on, when F2 finally gets invoked, bang, we're gone. Everybody get that? So what's happened is, underneath the covers, just so you can take a look, that's what a vtable structure looks like on the left. You've got a pointer in the object pointing over to the vtable, and that vtable contains the addresses for functions 1 and 2. Now what happens is when function 1, when the object gets freed, and I can't explain why, somebody actually is able to go in and spray the heap with code, attack code. So then what happens is, when we call that E1 source element function, we actually invoked a virtual method that had, which basically called the attack method. So we really care about security a lot. And we can't talk about it very much. But what if the compiler generated code to check basically that the flow was always legal, or if the stores were always legal, right? This is where type safety certainly comes into play, and it's heavily related to alias analysis. But in our world, static analysis that actually, or any kind of like a checked build wouldn't be enough. This stuff would have to be on by default all the time. It couldn't slow the performance down, and it would never be something that we could fully disclose. But this is an unbelievably great area for language designers, the hardware designers, and the compiler writers to make an incredible difference if we work together. This is super, super important. Okay, we talked about security enough, so I'm going to go on to parallelizing control flow. And the reason I'm going to talk about parallelizing control flow is a great example of where we missed an opportunity to work together, the hardware developers, the language designers, and the compiler writers. So this is an example of where vectorizing control flow would give you a 12% win on libquantum. Okay, so you've got two ifs. We could converge those, and we could vectorize. This is another example of where we could vectorize, and this is purely nested control flow that cannot be converged by source level tricks. This has to be handled by complex bit masking in the compiler. But if you actually hit this loop and you vectorize it, you'll speed up one of the numerical recipes 300%. But it's a great example of something really, really simple that requires a tremendous amount of vectorizer transformation and some bit masking technologies. So back in '97, a guy at Intel named Bistry came up with a great way to do what's called bit masking, or how to actually vectorize control flow. And the Intel architecture and its instruction sets evolved exactly from supporting this transformation that I'm going to show you. So if you were to abstract things out, what I mean by the if-then-else statements is the left-hand side sub I is equal to the right-hand side sub I. It's a great way of avoiding all the details for what would be in there. But what I'm going to try to do is, in order to explain the core concept, is I'm going to try to focus only on how you would vectorize that little bit right there. Okay? So before I do that, what we're going to try to do is generate a bit mask, and I'll explain what that means for if condition, and then that bit mask would control where the evaluation of that statement would occur. Okay? So that's pseudocode for create a bit mask and put it in some register. And now what happens is the left-hand side can be created without any control flow, and let me explain why. So the first part of that predicate is saying, what are the original parts of the left-hand side that I have to maintain? And then what are the parts that I can take from the right-hand side that evaluate it to true? So in other words, if that mask were false, I have to use the original values from the left-hand side. But I can put those together, OR them together, and then write them back to memory. So that's the instruction that allows us to generate the bit mask. That's a pairwise compare equals. So if we assume that the condition was an equals, and that's how the bit mask gets created. So that's the way we represent a vector Boolean, so to speak. So now, this is the first part of that predicate. In other words, wherever that mask was false, we're going to need to retain the original left-hand side. So when we evaluate that machine instruction, we're going to wind up with that in XMM1. So it means in two places, we are going to have to put back the old value. And then the second part of that predicate, that's where the condition was true, we're going to actually and those together, and that's the part we can actually use from the true evaluation. So we've got the right-hand side and the left-hand side values being glommed together under a bit mask, and now we don't have any more control flow. So then finally what we'll do is we'll OR those back together, and you can see that that result is 2 new values and 2 old values. So the language guys have to be tense here, I know it, right? Because what we're going to do is we're going to write back values, the original values, and that'll be semantically correct from a value point of view, but it's absolutely illegal now with the new semantics of C++. So that's what we would do to do the store if it were legal. And we really, really wanted to do this. We had the code written to do this, and it looked really fast, and it was glorious. But, so I stole this from Herb Sutter's slide deck, right? New fact of life, it's a multi-core universe, right? The system or the compiler must never invent a write to a variable that wouldn't be written to in a sequentially consistent execution. Anybody know why? Anybody want to venture why you don't want the compiler introducing stores where there were no stores before, even if you're storing back the old values? Yeah, race conditions, right? And if the programmer can't see all the variables that get written to, you can't possibly know what locks to take. So what's cool about the new C++ 11 is that you should be able to look at the source code that'll be executing on different threads and just reason about it as though it were executing sequentially. So the last thing you want is the compiler to be inserting stores, even if we're storing back old values. So if we look at vectorizing control flow in retrospect, this is literally what happened. So the hardware was designed, and the load and store instructions are not masked. So when you do the store, there's no way not to actually wiggle the bits on the bus and actually introduce stores where there weren't any in the original sequential code. The C++ language then was defining sequentially consistent semantics, and then the poor compiler vectorizer guy, Herb, Jim, wait. So that's exactly what happened in real time. We had the code ready to go, and I learned about this in real time. So this was a great example, again, of where the hardware guys, the language guys, and the compiler guys could work together going forward and have a huge impact. So we talked about parallelizing control flow, and now I'm going to talk about alias analysis. And before I go on, this is the one part of the talk which is the most forward-looking and is going to have the largest impact on everything that we're doing. So alias analysis affects all the optimizations that we do. It's hard for me to think of one that it doesn't affect. And one of the examples that I wanted to go into was security, and I'll get to that. So here's an example of what I mean by alias analysis. At the top is a store, at the bottom is a load. So if Q and P don't alias each other or point to the same locations, then what we can do is we can actually propagate 70 and get 100. Sorry for the typo on the screen. But C++ alias analysis gets a lot harder. And so now, if P is global, and that's a virtual call in between, we have to be able to figure out whether or not that call tree that emanates from that virtual call could possibly alias P. So alias analysis in C++ gets really hard, really fast if you want to be practical, because not a lot of things in C++ look this simple. A lot of C++ looks like this. So now we actually have to turn the compiler into answering that question, which is, what's the call tree point to? And that gets us into devirtualization. And it gets us into types. So if I was able to prove that that call tree could never possibly alias P, then we still could do the same thing. But C++ alias analysis, we feel, is really, really turned into something far more complex than it really has to be when you eliminate double indirections from the picture. So here's an example of where I want to show how double indirections can actually cause a real serious problem. If you look at the first statement, P equals new point 3D, we set up P to point to an object, right? Then we take the address of that pointer itself, right? And now we assign X to be pointing to some new object. And what we've just done there is we've changed the type of P. So here's the visual in slow motion. So P points to that pointer, a point 3D type. Then what we did is we took the address of P and we stuck it in X. Then we said what X points to equals new base. And so effectively what we did was we created that base object, got rid of that, clobbered that pointer, and now we changed what P points to. We basically changed out from underneath you what was going on. That's our terminology for when we're trying to track pointers and figure out what's going on. So we feel, going forward, types and alias analysis are an incredibly wicked cycle, and it's an incredibly important thing to actually invest in. This is probably going to have the most far-reaching effects on everything we do going forward, and it's really, really hard. So in this particular example, you can see if you changed what Q pointed to out from underneath you in this example, then at the very bottom, we wouldn't be able to track that virtual method in Q. So that Q foo no longer actually is what we can figure out. So if you're doing type propagation and you're worried about alias analysis, it forms a Mobius strip. Because we really need to know what things point to and what that thing is going to be calling. Make sense? So now, what we're thinking about doing is subsetting C++ at compile time. So what if pointer indirections were restricted? A pointer cannot be aliased to another pointer. If we do that, we could probably assure that there are no hidden updates. And what we could do is reject double indirection through a pointer that's had its address taken as a warning or an error at compile time. It's really hard to prove, but once you do this, the engineering of the alias analysis and type propagation turns into something that's a lot easier to do and a lot more predictable. So this is something that we're going to be we have been aggressively investing in. And it's really important too, because this is very similar to like in C# where you can't take the biref of a biref. What this does then is it allows us to eliminate a lot of runtime checking for security, because then we know things are type safe, for example. Or we're actually able to do a lot more with vectorization because we've been able to propagate just simple loop bounds. And it goes on and on and on. But this is, I thought, was a really interesting part of what we're investing in. So alias analysis and type propagation in that Mobius strip affects all core technologies that we covered. It affects our ability to do stack packing and code size optimizations, vectorization, security, parallelizing C++ control flow. And it has an iterative effect on our ability to do interprocedural alias analysis. And most importantly, this all is for all of these technologies improved affect all hardware and all runtimes that we target. So we talked about how we worked. We talked about all the core technologies that we care about. And I talked a little bit about where we're going in each of these areas. And I was hoping that you could see the processor roadmap in conjunction with our compiler plans, because we're right here right now. And this train is charging ahead really quickly, not only in the Intel AMD space, but also in the ARM space. So the compiler not only has to evolve those technologies to get better performance, better security, better compile time, but it also to make effective use of this new hardware that's coming out literally faster and faster than I've ever seen in my career. So in summary, I hope that you've all seen the true size and scope of compiling C++ at Microsoft with all the different graphics that we had for building Windows. For programmers, I hope that you saw some of the core technologies that we work on and some of the issues that you might be able to avoid at the source level when you're writing code. And then for hardware and system designers, it would be really great if you just came up to Redmond maybe and worked with us directly if you had the time. I think that there's an enormous amount to be had in security and also being able to speed up parallelism. And that's about all I had to say today, except for, one other thing I wanted to say. A lot of what we do requires a really great team. And one of the things that I'm fortunate to have is a great bunch of coworkers. I've been at Microsoft for about 15 years, and there are a couple of guys on the team that have been with us on my team for a long time. And I wanted to say thanks to Ian Bierman, Eric Brummer, Mark Levine, and I hope those are the people that have been with us, and Shane, those are the people that have been with us the longest, and I wanted to say thanks to them, and I'm really fortunate to have such a great team to allow us to attack this. So thanks, guys. So any questions?
Good. All right, Vlad. Hey, that was excellent, man. It's good to get that level of depth, because this is really what goes on underneath the code people, right? So
when vectoring conditional statements, why can't you use a masked store?
Because the hardware doesn't support it.
Okay.
That was really the point of why it would be great. It was an example of where if the hardware designers, the compiler writers, and the language designers had conspired together earlier, we might have had that. And there is rumor that the hardware is going in that direction.
Are there any plans for migrating the kernel to C++ from C? Because you could probably get some significant improvements in reliability and so forth that way.
It is in C++?
No, it's in C.
No, there's tempted meta programming in the kernel.
It's scary, but that's true.
Runtime, yeah, but there's no exception handling. I'm talking about the runtime. You cannot write C++ generically in the kernel. So, is there any prospect of changing that?
I think that, it's slowly evolving in different places, but, where we need to have the structured exception as a paradigm, I doubt that those areas are going to change.
Hi, what happened to the Phoenix compiler?
What's really great, so we're heavily weighed down with actually, maintaining correctness at all times and constantly delivering the new OSs and a lot of the new applications. And it's really great to have another compiler team doing research. And so what they're doing is advancing the state of the art in a whole nother area, which is incredibly important to the company.
Next question.
You spent a lot of time discussing how you had to fix the compiler, change the compiler to optimize existing old style code and make it fast and secure. But what about for new code? With what you've learned, do you have like a list of recommendations of things you should do or should not do that makes the compiler job easier? For instance, should we use Valeray? Does that help the compiler? Does it make it better, safer? Or is that something that we shouldn't be using?
What we'd like to do is just try to make sure that you use the language as it is today and put the burden on us to do the right thing. The concepts that I've talked about are really the concepts that should apply. If you make the alias analysis for the compiler harder, we're going to give up. If you use constructs that are really difficult for us to cons up a new symbolic expression on any load or store, we're going to fail to vectorize. All these concepts really should fall out right away from when you're writing the code. So
Right.
I don't want to restrict the language or actually, prescribe how you would want to write code.
Right.
It's really upon us to support what the language abstractions are, which are supposed to make things easier, but at a different level of abstraction for the programmer.
Right. Does using Valeray help?
Not really.
Not really. Okay. Thanks.
I'd like to ask two questions. The first is, how do you approach competition, or do you approach it at all?
Competition?
Yeah, in compiler space.
Wow. All right, so I'm a guy, right? So there's a part of this which is pride, and there's a part of this which is practical. So it's difficult to expect a lot of compilers to compete with us in being able to compile the Microsoft stack, right? I mean, there are parts of the compiler in the front ends that are 20 years old, and we've been able to amass an incredible amount of experience in how to compile large source bases while innovating in the compiler. And it's difficult for me to imagine a lot of teams being able to have the assets that we have at this company in the correctness and throughput space. And we also focus tremendously on a lot of obscure things that a lot of other compilers wouldn't focus on. For example, I don't know how many compilers will angst about stack packing, right? But it will matter to us because that's startup time for the kernel. But then what happens is we get blasted in the press when you see these new benchmarks that come out, right? We may or may not think that that's strategically important for the month of July in 2013 when we're trying to get 4 more cache lines saved for when we're actually walking the DOM, right? So that's a long-winded way of saying we don't worry about compilers competing with us on correctness and throughput just because of what we have going here, but we do care a great deal about when we get lit up in the press for the benchmarks.
But from the language perspective, like new features are being implemented in GCC, for example, first, and Microsoft compiler doesn't look that good from that perspective.
New language features?
Yep.
Oh, okay. Well,
The back end.
You want to take that? Jonathan?
I mean, yeah, we're making progress that definitely, and we've heard talking more by that tomorrow.
Okay, and the second question was about.
Let me back my brothers up on this one. All right, we are. So the front end team has it really hard too, right? Because what the front end has to be used as is a command line compiler. Then it has to be able to change modes and be able to work in the IDE where it can actually parse completely wrong and incomplete statements. And then it has another third area, which is it has to be the expression evaluator and the debugger, right? So the poor front-end team has a tremendous nut to carry, which is that it's used not only just for being the front end for C++, but that said, we are aggressively hiring on the front-end team and adding features, I would say, faster than we've done since I've been at Microsoft.
So I want to ask you a question about kind of the last thing you're talking about. You're talking about subsetting the language, which is a very bold move.
No, it's derived. I don't mean to actually. I mean, we'll derive whether it has been subset by the program that we're analyzing.
Okay. Can you be a little bit more clear about, like, can you be more specific about what you're looking for here? I'm really interested.
Pointers to pointers.
I don't want to take the address of a pointer, right, that's going to be used in a double indirection. And it's exactly equal to in C# where you can't take the biref of a biref. That's the most concise way I can say it.
Okay. Is this something that you want to do globally or locally?
Globally. Absolutely globally.
Okay, so you have to be able to say that, globally there's no point at which you have a pointer to a pointer being formed.
Yeah, that's one way of saying it, but you can make it more concise. The goal is to crack that vicious cycle between type propagation and alias analysis, right?
Sure.
So the engineering becomes gets simplified and more predictable. Instead of tracking, does P and Q point to each other, now all of a sudden you got that next level, which is does star P and Q alias the same thing?
Okay.
So I had a question about that same double indirection. So in Windows, like for example DirectX, there's a lot of times where you like construct COM objects using double indirection. Will there be some special case to still support like the legacy Windows APIs, or maybe not even legacy? I don't know.
Oh yeah, I mean, bottom line is we can't break anything, right? We have to compile the existing universe.
Yeah.
Completely, all the time, actually, every day at 3:30.
Well, I guess so. Yeah, you still have to compile it, but will you still try and optimize, for example, a special case of like constructing a COM object where you have this double indirection?
Yeah, of course.
Okay.
Really? Ah.
I have actually a couple of questions, but I'm curious, since you're the back-end guy, what is the input that you get when you start doing the optimization work that you do? So, I mean, do you have all the type information? Presumably you're not looking at the syntax tree or something. So essentially, what is your input? And the second thing is, under the assumption that someone's compiling or actually building with whole program optimization, so you have essentially global information, what can you do in terms of things like automatic inlining, devirtualization, and then the corresponding dead code elimination that would go along with devirtualization?
Okay, let me tackle that backwards so I don't forget. We have a team that's dedicated to whole program analysis. We do what we call link time code generation. So what we'll do is we'll serialize the IL that's been handed to us from the front end and create object files that just contain the CIL out of the front end. And then we'll go back and we'll create a global call tree. And then we'll use that global call tree to first propagate information up and down, attributes about types and alias analysis. And then we'll compile that bottom up. And that's after we've done the inlining. And a lot of the inlining isn't really effective unless you actually run profiling. So especially on x86, where it's real easy to blow out the registers, we have found that you really, really need to have profiling information for the frequencies for the call sites. So that's a huge framework. It's different than the scalar optimizer, and it's something that we're aggressively investing in as well. Does that answer that part of the question?
Well, do you do any automatic inlining by default? Because I was under the impression that you did, even without PGO.
Oh, yeah. We do a bunch of heuristic inlining. We'll even inline finalies. We'll inline functions. But it's all done heuristically. And what you'll find is that that's very fragile, especially when you've only got 6 registers. And so we go really conservative on the heuristic inlining.
Okay, and what about devirtualization and then dead code elimination, for example, if there's derived methods which you can prove are never called?
Yeah, so the tree shaking is something we're doing in another framework that I can't talk about right now, and I get that. But devirtualization is something that we've started down. We have minimal devirtualization in the shipping compiler today. And getting that absolutely right has turned out to be much harder than we really expected, because types can escape or types can be defined in other DLLs. And so right now we do it, but it's limited, the devirtualization.
Okay.
And what was the first question?
The first question is what essentially what is the input that goes into the back-end optimizer?
So the C++ front ends just basically serializes its trees into 5 simple temporary files that we then in the back end will crack and read in, and we'll reinflate our we go from their trees to our quads, and then we get their type information through if it looks like it's going to be a win, and then we also use another one of those files to inflate our symbol table.
So you do have type information available to you if you want it?
Yep.
Okay.
Aha. Let me go with the guest and then the master.
Would C99 support completed harm your department?
No.
Good.
I always
Thank you.
like imaginary numbers.
One excuse gone.
Wait, did I get the wrong answer?
For devirtualization, I think you can mention that you and the front end conspired that if you mark a virtual function as final and it's called through that derived type, I believe in 2013, we get devirtualization. I remember asking for that, and my wish was granted. So final
Is
does do
Patrick
that.
here? Can you answer that? Yeah.
Okay, it is. So yeah, that's what I thought. So we actually will respect C++ 11 final, which is cool.
Yep.
Nice.
Thanks.
Any more questions? Okay, so it's 5:30. Jim, thank you so much for coming
thanks,
down,
everybody.
man. It's awesome.